Get started when you're ready.
Okay. Hello everyone, my name is Sunbeom, and today, first, I'm very honored to be presenting here, and this is my third document. And I'm going to be presenting about the how to advance shark tracking with computer vision systems. So before I jump into the technical detail about shark tracking, I'd like to discuss briefly about the motivation of why we want to do the shark tracking. So we collaborate with the Shark Lab at CISO, and well, obviously this picture you can't really tell if the shark is like offended or dangerous. You cannot really tell, but with utilizing the computer vision and the shark tracking, we can actually tell if they're happy or not and have negative reaction to the human or not. So that's the research that we're kind of focused on. And this is more a detailed example of how we can classify shark reactionary behavior. So first we need to extract this shark tracking results, and this is the computer vision part that our lab was working on. And after we extract all the tracking data, we can build the behavior graphs, which is distance, speed, and angle. And according to the Shark Lab, if we have these graphs, we can fit this graph into the metrics that we call behavior, shark reaction and behavior metrics, and we're gonna find the row that is gonna match with this behavior graphs, and apparently the shark has no reaction. So that's the motivation of this research, and I'm gonna be talking more about the technical details about the shark tracking. So in order to extract the shark tracking data from the video, we need to apply one of computer vision tasks, which is object detection. And object detection can be broken down into two main components, which is the first one is image classification, and the second one is image localization. So image classification will tell if the image is like either shark or human or boats. Image localization will be able to tell where the object is on that image. And obviously those two techniques require lots of computational powers because we need a neural network to train. We need lots of images to process to train the neural network to classify the objects, and also we need to apply sliding window techniques to image localization. And sliding window techniques needs to apply lots of filters to one image and breaking down into several pieces of like an image, and then need to input that to the neural network again, and apply different filters over again. So basically, we need lots of computational power with it, and to advance the shark tracking, we need to enhance this neural network. We need to find a way to enhance this neural network. And the first approach that we used to enhance our neural network was using convolutional neural network, which is called CNN. And it optimizes the training and predicting procedures using less weights and sharing the parameters. So obviously we can see that the traditional fully connected neural network uses lots of weights, and lots of weights means there's more computations. But convolutional neural network, since they're sharing the parameters, they use like the less weights. So it's more efficient over to fully connected neural network. And the second approach that we use is you only look once approach, which is called YOLO. So the YOLO is CNN can leverage the sliding window techniques really efficiently, but YOLO can do much more than that. So we divide the we divide the images S by S grid, and then we're gonna be applying like prediction for each crystal, and each crystal we will roll out with the bounding boxes in the confidence, and we can merge them into the final detections. And this is much more efficient than sliding window techniques using CNN, because sliding window needs a filter and needs to apply different filters and need to do the same computation over and over again, even though it shares the parameters. But as you can see in here, the times of computation that we can apply in here will be only be S squared times of computation. So this is much more efficient. And this is the network design of the YOLO. So it utilizes like convolution network a lot. Apparently like a 20 more convolution network. And then it uses the fully connected network to classify the results later. So this is a tracking program implementation that we created. So the left side is like the flowchart of the Python program. I'm not going to be like going over detail of the procedures, but the important part in here is that this is only possible because we use the YOLO program that provides the RoboFlow. Because like the video, like we're parsing the video and like we're breaking down the videos into several frames, and that's like lots of images to process. And since YOLO is like very fast at detecting the objects per image, we're able to accomplish this like tracking. We're able to extract the tracking information almost in real time. So this is the result that we got from running the program. So as you can see, the chart has the green box and it draws a tracking line. And the yellow part is that where the YOLO could not detect the sharp objects, but we use the bounding box detection and the linear interpolation to connect those lines so that we can complete the tracking line. And the next one is it does not really detect the shark really well because it's not really perfect. If the object's like too small, it really struggles to detect the shark. But eventually it's gonna detect some of the shark objects. But this is just something that we need to will improve for the future. And hopefully you guys are enjoying this. Yeah, so this is pretty much it. And thank you for listening to my presentation. And I'll be happy to answer any questions you guys have.
Got one for you. Did you check any other kind of procedures outside of the YOLO? To see if there's any other things that might be able to do the same thing?
Yeah, sure. So YOLO, we decided to use YOLO because it's really good well processing the images like that has like overlapping parts because it uses the convolution network like all parts. So it's very efficient in that way. That's why we chose YOLO. But there were other candidates as well, such as
SAM.
Oh, SAM. So like we were trying to use a SAM segment anything, and I forgot the end part. Yeah. So SAM basically detects all the possible, it segments all the possible objects, and we were trying to utilize that to track the shark as well, but it was too slow for our machine. Even though we had like a 2 GPUs on that machine, it could not really like function well. So we decided to just stick to the YOLO, and for the future usage, probably we can leverage more with the SAM and the YOLO together, because obviously the orange line that we saw, we kind of failed to detect the sharp objects that specific frame. So maybe utilizing the SAM could like help us more to like detect the sharp objects like more precisely. Any other
Did you play around with the parameters for the YOLO model, or did you just use it out of the box, or like you change any of the optimizers, or activation functions, or loss functions?
So basically, I did not really like change anything with the structure or like the class that it provided by Workflow, and the training part was done by someone else, and I was like using the pre-trained model, and the Workflow already has the tool to train the models. So, and I just like received the pre-trained model and I focused on the Python programming parts, drawing the tracking line, extracting, actually interpolation part. So.
Yeah, I use YOLO ones too, and I just use the defaults because it worked perfectly. So
Yeah, it's kind of tricky. Yeah,
Yeah.
it's fast. It's really fast, but it misses the object like a really like often.
yeah.
So you gotta be really careful of using it. That's why we haven't used the linear interpolation and the object, the bounding box